When we were discussing bounce diagrams in some of the previous videos, we showed that for a line that had a mismatched source to characteristic impedance of transmission line to load, what happened was at these impedance boundaries we saw some voltage reflections. We saw that there was a reflection coefficient times the incident wave that got bounced backwards, and then we would have reflection coefficient of the source times the reflection coefficient of the load times the incident wave, etc., etc. And we would have this mismatch at both ends. This impedance mismatch at both ends would result in transient voltages that get bounced back and forth. We also showed that if you take this solution logically far enough in time, that these bouncing reflections eventually settle out and we get to steady state where we would get a voltage divider between the battery voltage, the load, and the internal impedance of the source. If instead we want to turn our attention to what happens if we connect a sinusoidal source to a transmission line, which is the primary purpose of RF analysis. Remember, we're looking at high frequency RF signals. If we were to analyze this, which we will do, what we would find is that instead of this DC response that we showed with lots of reflections, we're going to find out that given enough time, the voltage and current along this transmission line are going to exist of one single voltage wave traveling from left to right and one single voltage wave traveling from right to left. So the final sinusoidal voltage wave can be expressed in terms of one single forward wave and one single reverse wave. And the same can be said about the current. And what we're going to do through a lot of these videos is actually prove this. And to do that, we're going to just apply Kirchhoff's voltage law and Kirchhoff's current law to a differential element of a differential segment of transmission line. So here what we've got, just to kind of remind you, is we've got the distributed parameter model for a lossy transmission line. Here R prime represents the series resistance of the conductor per unit length. That's R prime. L prime is the series inductance per unit length. G prime is the conductance of the insulator per unit length. And C prime is the capacitance between the two conductors in the transmission line per unit length. So this is in ohms per meter, henries per meter, mhos per meter, and farads per meter. If we take any of these distributed parameters and multiply them by the length of a differential segment of transmission line, we get total resistance, total inductance, conductance, and capacitance, etc. So what we've done is we've taken a very short length of delta Z, meaning one end of the transmission line is at a distance Z, and the other end of the transmission line is at a distance, so we've got this distance Z, and the other end of the transmission line is at a distance Z plus delta Z. So the total length of this transmission line is just delta Z meters. So again, the total resistance, the total inductance, the total capacitance, and the total conductance is just calculated by multiplying the distributed parameters by the differential length, delta Z. So now what we want to do is apply KVL to this tiny, really infinitesimally short segment of transmission line. And so Kirchhoff's voltage law, KVL, we just sum the voltages around a closed loop and they equal to 0. So the closed loop we're going to analyze is this loop here. The input end of the transmission line, the series resistance and inductance, and then the output end of the transmission line. So that's one loop right there. So if we were to write KVL, we would say that the voltage at the input end of the transmission line, V of Z comma T, is equal to the voltage drop across the differential R prime plus the voltage drop across the differential L prime plus the voltage at the output end of the transmission line. So I know that looks simple, but that's a complete statement for Kirchhoff's voltage law along this differential segment of T-line. If we were to calculate what VR prime is, well, that's just a resistor, so we use Ohm's law to calculate that. It's going to be the total resistance, which is just R prime times delta Z. So this quantity is total resistance, and we need to multiply it by the current that's flowing through it. Current flowing through here we've indicated is I of Z comma T. So that's VR prime. What about the voltage drop across the inductor? Well, the formula for, and that's just V equals IR. It's just in cosine form. If we were to extend that to the inductor, VL prime is going to be equal to the total inductance L prime delta Z times what we call the partial derivative with respect to time of the current flowing through the inductor. And what that is V equals L di dt. And so the rule for the voltage drop across an inductor is that we take the inductance of the inductor and we multiply it by the rate of change of the current. So this terminology might be a little unfamiliar to you. This is the partial derivative. It just means take the derivative of this function with respect to t and not with respect to distance. Remember that our currents and our voltages for traveling waves have two independent variables, distance and time, and so when we differentiate or integrate, we have to do that with respect to one or other of those variables, and this is telling us take the partial derivative with respect to time. So we can substitute these statements into our KVL, and I will do that. So we have V of Z comma T, the voltage, the input voltage to the voltage across the input end of the transmission line is equal to the voltage drop across the differential resistive element, which is just the total resistance times the current. And then the voltage drop across the inductor, which is the inductance, times the partial derivative of current with respect to time. And then we have to take the voltage drop across the output end of the T-line, which was just delta Z meters further along. So that's a complete KVL statement. And what we'll do now is we'll just convert it, we'll make it a little simpler to write, we'll just convert it over to phasor form. So we'll write that in phasor form. And to do that, we're going to just remind you, I'm just going to remind you that if we have a phasor notation, we have the amplitude, e to the j omega t. Oop, I put a bar over that, that's not true. It's a plus, so it's the peak value, e to the j omega t, e to the j beta z, e to the j phi. So we've got the time phasor, the distance phasor, and the phase shift. And we showed a neat trick that if we take the partial derivative with respect to time of that phasor, a of z, that is this, we just take the derivative d dt of e to the j omega t, and then we multiply it by a plus e to the j beta z e to the j phi. So I'm just taking the derivative of the phasor voltage or phasor quantity there, and this is nice. This is one of the reasons we like to use phasors, because the derivative of e to the j omega t is simply j omega times e to the j omega t, and then we can just multiply by a plus e to the j beta z e to the j phi, and so that gives us the derivative of this phasor, or the partial derivative of the phasor. So what you should notice here is that this quantity here is just the phasor quantity, and so the partial derivative with respect to t of a phasor quantity is just j omega times the phasor quantity, which is one of the reasons people love to use phasors. And we can plug this result, we can use this result to simplify this equation in phasor form, because we have this differential, this partial derivative that we need to take here. So if we were to write that in phasor form, we would get V of Z, the phasor voltage, is equal to R prime delta Z, again that's just total resistance, times the phasor current flowing through the resistance, I of Z, plus L prime delta Z, which is just the total inductance. And now we have to have the derivative of the phasor current, which from this result here is just going to be j omega times the phasor current, I of Z, and then we need the phasor voltage across the output end of the transmission line, which is just plus V of Z plus delta Z. So now we've been able to rearrange that into phasor form.